So, welcome back to this second half of this this lecture. One more example I want to write it. This is just reminding you that you have studied similar stuff there in college, but without not in this notation and not in this thinking. So, this is called conic sections. So, if you go back to your college days and remember you were studying a polynomial in two variables f of x y. We were one polynomial, no, I called variables the letters not x1 x2 but x and y. So, this is a polynomial in two variables x y over the field of real numbers, and we were assuming that it is irreducible. This word I think you know it, irreducible over R. That means you cannot factorize this polynomial in two different factors, two different non-constant factors. So, such a polynomial is called irreducible polynomial, and actually it is not necessary to assume this irreducible, but those that time some vocabulary was not studied properly in the college days, therefore, they were making that assumption to make simplification simpler. Okay, so, and what are we looking for? We are looking again for solution set or reals again. See, those days this is very old, this if you know this goes back to the Greeks. So, these we are real solutions of this polynomial f, this is f. These are a comma b real numbers in R2 such that f of a b is 0. Then we prove, this is proved in college. So, we proved this proof was not so simple given in a college days, because there were a lot of things were coming and every time we were making shortcuts, simply because the concepts were not available at that time in the college curricula. So, what we did was, so there exists a change of variables now what does this mean? This means we can change these variables x and y. Actually, strictly speaking, it was a linear change of variables. There exists a linear change of variables. So, that means you change x to some lambda x plus mu y plus a constant, and y to lambda prime x plus mu prime y plus nu prime. So, that when you say change of variable, so that means from this new, if you call this as x prime and this as y prime, from this x prime and y prime you should be able to recover back x and y. That is equivalent to saying, if you look at this matrix, so the matrix lambda mu lambda prime mu prime, this should be invertible matrix, so that we can get back your x and y. And why, how do you do this? I will not repeat that process here, but what was the need to do this? So that this polynomial looks simpler. So that f looks like f the new, when I make the change of variable, new polynomial f prime is f of x prime y prime will look like, there are 3 cases, y minus x square. So, now the new variables also I call it x. So, the new polynomial will look like y minus x square or xy minus 1 or x square plus y square equal to 1 . It will look like this, one of this. And now what was the advantage? One more case I forgot, namely one more case, x square divided by a square plus y square divided by b square equal to 1. So, these are the 4 cases. Now, what is the advantage of this? Now, let us see how do plotting is much easier now. So, in the first case, unfortunately I have to go to the next page. So, in the first case, this case y minus x square, what is the 0 set? If you want to plot now in the real plane, this is R2. So, it is y is always positive. So, it is like this. This is called a parabola. In the other case, xy minus 1, xy minus 1 case, it is this is not touching here. This is called rectangular hyperbola. And in these cases, x square plus y square equal to 1. So, this is a unit circle. This is a unit circle, usually it is denoted by S1. And in the other case, x square by a square plus y square by b square equal to 1. This is the same like circle, but it is the axes have the different. This is called ellipse. The major and minor axis A and B there. So, when so this is A, this is A and this is B. And then we were studying these geometric figures by using the algebra. So, for example, we were from this equation we were deciding what is the tangent, what are the normal, their equations and so on. So, we were studying geometry of these pictures, and that was already quite a bit, but we were doing it more mechanically. There was no substantial theory, and that was the reason why it was very limited to 2 variables, and that also to degree. I forgot, let me go to the earlier thing. I forgot to say that degree of f is 2. This I forgot to make this assumption. So, we were only studying degree 2 polynomials in 2 variables, and already that study of the geometric pictures, geometry of these pictures, that was already complicated, because first of all, when given arbitrary equation, arbitrary polynomial in two variables of degree 2, we had some recipe to convert that polynomial to one of this, and already that was using some linear algebra and some calculation to decide that, and then we are studying the normals, tangents and so on, a distance and so on. Also we had studied from the pictures how to get the equation. So, suppose your picture of the parabola was not like this, but suppose it is, this is not touching the x axis, but it is something like this, then what is the equation? Or it is somewhere else, it is here, then what was the equation? And similarly for circles, hyperbola. So, if hyperbola was not like this, somewhere else, suppose it was like this, then what is the equation? And the definitions of parabola, hyperbola, circle and ellipse, they were also given not using the polynomials, by using some invariants of this like eccentricity, directrix and so on and so on. So, the study was not very uniform, or study was not theoretically it was not sound. So, therefore, that is one reason. So, it needed more theoretical. Alright. So, if one tries to do it for, you can keep the polynomial in two variables only, f equal to f x y. So, there were, roughly speaking, there were 4 cases in when the degree f was 2, and when the degree f is 3 now, then it became much more complicated. There was an analysis available which was done by Newton, and there were about 78 cases. So, that was too much complicated. So, anyway, these were the days when 17th, 18th century and so on. So, subject needed more revision, and they needed more tools to study this, and the tools only came in later half of the 20th century, that is, let us say after 1940. And this basically happened because commutative algebra was introduced during this time, and also it was introduced with the view in mind that studying geometry it will help. That was one reason. At the same time, a number theory was also stuck like that. Stuck means the study was complicated, and people have realized, people like Noether, Dedekind, Hilbert, etc. They realized that if you study commutative algebra, that is also very useful for number theory. In fact, for number theory, the commutative algebra use was only so called one dimensional case, because they arise as only curves. So, the algebraic geometry is even more larger than these subjects. So, and in this course our aim is to integrate both these courses. So, a large number of lectures I will have to digress what is called commutative algebra, and for that I will have to introduce little bit more general setup. So, what is that we are going to do it now. Let me now set up a formal notation which we will use. So, to start with, K is a field, and as you have seen, if I take polynomials over a field, it may not have any solution in with coordinates in K. Then what do we do in these cases? So, for example, we saw k equal to r and then x square plus 1, there is no real solution. So, in order to avoid this, one remedy is to assume, one possibility is assume the field k is what is called algebraically closed. What does that mean? Let us recall that. That means, so this means, so that is, if I have any polynomial f in one variable with coefficients in k, for every polynomial there exists a solution in k. There exists small x in k such that f of x is 0. So, such a thing also I will keep calling, that is x is a 0 of f. So, that is for example, a typical example of algebraically closed field is k equal to c is algebraically closed. This is not so easy to prove. This is it's called theorem of Gauss. Gauss has given first complete proof in 1898, but actually it was stated by D'Alembert. In 1746. So, if you go to see French book, they will say it is a theorem of D'Alembert. If you go to see German books, they will say it is a theorem of Gauss. If you see English book, they will say theorem of D'Alembert Gauss. I do not know whether I will prove this fact in this course, but certainly if you see my course on Galois theory, in January to April this year on NPTEL. This will have all the proofs of this nature, because it was basically a course on solutions of polynomials in one variable, how to solve polynomials in one variable, or what does one mean by solvable by radicals, etc. So, that was, I will strongly recommend for those who want to see the proofs of this algebraically closed, C is algebraically closed. It certainly it's there, it is not so trivial, but complete proof is there. Okay. So, that was one remedy I suggested, so that the problem of if you have one variable polynomial, then the 0 set is definitely non-empty. So, that we have some set to work with, it is not empty set. Alright. So, this is one possibility. Another possibility, second possibility to overcome the remedy is, if I have a field k, then there exists a field L such that K is a subfield of L. This means that this I will keep saying that L is an extension field of K, or I will also keep writing L over K the field extension. This simply means L is a bigger field That means the plus and dot in K are extended to L, the same plus and dot operations are there. They are more, they are on the bigger set. So, such a thing is called a field extension. So, this says if K is a field, then I can always find a bigger field such that L is algebraically closed. So, for example, for R, we already have C, this is algebraically closed. So, C over R, so for if K is R, then I can take L equal to C. If I have Q, well, C is also an extension of Q. So, I could also take C over Q. But this may not be the smallest algebraically closed field which contains Q. So, there is also a concept called algebraic closure. Of a field K. That simply means it is a field extension, the smallest field extension of K such that L is algebraically closed. Even such a thing exists. So, exists and essentially unique, essentially I will write here, essentially. This is again a theorem which again I will recommend you to see my course on Galois theory. This is proved there, NPTEL January to April 2019. All right. So, so the second remedy is you consider a pair not only K and fix a bigger field L. So, the bigger field is algebraically closed, and with this now we can make nice definitions and then we will play with those sometime. Okay. So, now definition. So, K is a field, arbitrary field, and F1 to Fm are polynomials with coefficients in K. So, that means they are polynomials in the polynomial ring over K in n indeterminates, and then we are looking for a solution set, but not with coordinates in K, but coordinates in L, and so L over K field extension L algebraically closed. Then we are looking for this notation V L F1 to Fm. This is by definition all those tuples x, x1 to xn, not in k power n but L power n, such that all these polynomials vanish at x. For all j 1 to m. This also I will just write fj of x, x is a tuple. So, this is a subset of L power n. So, for example, you know the difference, note the difference. If I write V R of x square plus 1, this is empty set, and V C of x square plus 1, this is plus minus imaginary I. So, this is the difference. This is because we do not come to empty situation, we have to go on with geometry. All right. Now, first note is this common solutions in L power n, that is also by obvious. Earlier also I remarked this is the common solution, therefore it is intersection over J of Fj V L Fj. So, here also in principle we could understand this set solution set better if we know for one variable, not one variable, for one polynomial in several variables, but the problem is also to understand intersection. So, understanding intersection, I will just say the following. See, suppose I would have taken what do I mean by understanding? So, suppose I will illustrate over reals first. So, VR of let us say y minus x square. Now, this is a parabola. So, this is all those tuples x and y in R2 such that y equal to x square. And suppose I take, so now we will say I will draw the pictures. So, this is my parabola, and I have considered this parabola, and now I consider another one VR of y. This is the tuple. These are which tuples? This is y is 0. So, this means it is x axis. So, this is all those strictly because we are looking in R2. So, this is x comma 0 as x varies in real numbers because y is 0. So, if I want to draw the picture together with this, so it is this one. If I would have taken other line than the x axis parallel, then it would be this. So, I should have used a different color. So, what is the common zeros of these two first? These two is only this point, and these two, if I have used the blue color for this, what will be the common zeros? It is this and it is this. There are two now, and here it is only one. Now, this algebraically you do not see this, but geometrically when you see it is seen. So, how do you prove this? Obviously, you cannot just the picture does not give the rigorous proof, picture only gives the intuition. So, when you try to write the proof, you have to write an algebraic proof, and that is what one mean by understanding this intersection. So, understanding this intersection can be very complicated. Now, this is happening because this y equal to 0 is a tangent line. So, it intersects only one point, and that point should be actually counted twice. So, how do you prove such a thing? Rigorously one proves. I will just indicate the proof quite quickly, because so rigorously how do you prove? We have this one equation y minus x square, this is our f1, and f2 is y, and what do you do? You eliminate y between these two equations. Then what do you get? That means you take y equal to x square and put it in this, right. So, here you do not see much, but if you let us take x equal to 1. So, do not take not x equal to 1, this is y equal to 1. Instead of this, I would prefer to take, that gives a better illustration, y minus 1. So, what is the, how do you solve this together? You put y equal to 1 in this This is y minus 1 equal to 0, that is same thing as checking putting y equal to 1, and when you put this equation, this y equal to 1 in this equation get transformed to 1 minus x square equal to 0. We are looking for the solutions here. So therefore there are two solutions. Otherwise what do? You put y equal to 0 in this equation and then you get x square equal to 0. But x square equal to 0 means x is 0, but that will come twice. So we have to check that the quadratic equation that has how many zeros. First of all, if I would have taken this line x equal to minus 1, then there is no solution, common solution, as you can see. But you cannot write the proof, this is not rigorous proof. So real rigorous proof is eliminate one variable and get a equation in only one variable, but because the degrees are 2, when you eliminate one variable you will get a quadratic equation in one of the variable, and then we know from the study of quadratic equation either it has no 0 or 1 0 with multiplicity 2 or two different zeros, that means each with have multiplicity 1, and therefore this picture gives you idea how to prove. And then conversely, this is a typical interplay between algebra and geometry, but this was very simple case and we have to go long way. So we need much better machinery. Okay, so I defined this set and we want to study this, and what is our machinery? We have only to start with a polynomials in m variables over a field k. That is the only machinery we have so far. Okay. So going back, this VL this VL of F1 to Fm, this is a subset of L power n. This is called affine algebraic set over K. Over K means simply to remember that the polynomials have coefficients in K, but this solution set is in L power n. Now we want to come back in some way like algebra. So what is the algebra involved to study this, and what is the geometry involved to study this? This is what we have to make it very clear. So algebra involved is, so we started with polynomial ring in n variables over K, and we started with m polynomials. Now I want to remind you there is something called ideal. This we have noted that this is a ring, and if I say ideal generated by F1 to Fm, this is the ideal in Kx1 to Xn generated by the polynomial F1 to Fm. What does this mean? This means you take all Kx1, x2, xn linear combinations of these polynomials. So that means G1 F1 plus Gm Fm, this collection of such linear sums where allow G1 to Gm not only constants but allow them to be polynomials again in the same variables. And this collection forms an ideal in this ring in K y1 to yn, not y1, x1 to xn. Now, let us quickly recall what is an ideal. So, if in general if I have a ring R, R is a ring, whenever I say ring, always commutative in this course. If I want to say any time non-commutative ring, then I will specify, but if I forget, ring for us is always commutative ring. And what is an ideal? Ideal, that is, I will write this Gothi K, this is a subset of R such that there is no underline there. So, this is a Gothic, this is Gothic letter which corresponds to the letter A. So, therefore, I keep calling it. This is because of the Dedekind. Dedekind was the first to introduce ideals and studied ideals and so on. So, what is an ideal? First of all, under addition, it is abelian group, abelian subgroup of R plus, and it has a property that if I take any element A in R and any element x in A, then A times x should be in A. Then such a thing is called an ideal in the ring R. See, it is more than a subring. Subring just means that under addition it is a abelian group, under multiplication it is a submonoid and so on. So, this is an ideal, and note that it is very much from the definition it is clear that this set, this solution set does not depend on these polynomials, but it only depends on the ideal generated by the polynomial. So, this is same thing as ideal generated by this. And what does one mean by this? This right hand side is, that means this is the set of all x, x1 to xn in L power n. These are small x. So, one has to be careful writing the notation small and capital X. So, this is small x, that is why I write this tag, little tag. So, this small x. So, all those points such that h of x1 to xn is 0 for all h in the ideal f1 to fn. This is very clear because you see, because if all polynomials in the ideal vanish, then all polynomials fj's vanish. So, this is definitely clear. Conversely, if you have all these polynomials f1 to fm vanish at that x, then the linear combination of f1 to fm with coefficients in the polynomials will also vanish, because you see, if I want to evaluate such a combination at x1 to xn, that is same thing as g1 x1 to xn times f1 x1 to xn plus g m x1 to xn times f x1 to xn. Such a combination, each one of them is 0. We are assuming that x is here, then each one of them is 0, therefore, this combination is 0. So, therefore, we have proved this inclusion also. So, in other words, this you can more generally define the affine algebraic set by defining it for any ideal, and then we will continue this study in the next lecture, and I will have to digress some more algebra, because algebra gives more precision, geometry is more intuitive, but it is less precise. So, while writing the proofs we will be more precise by using algebra only. So, I will stop here and we will continue in the next lecture. Thank you.